Alright, welcome to Mathman Academy. So in our previous class we started with thermodynamics, MEE 206. So we had introduction, it was an introductory class where we discussed about the introduction of thermodynamics, the systems that, as in considering thermodynamics to be a system, and the type of systems that we have. We have the open system, closed system, isolated system, and it can be in form of homogeneous and heterogeneous systems. Is that taken? Then we further to discuss the processes that we have in thermodynamics. Is that taken? Where we consider when there is addition of heat at constant temperature, that's isothermal, at constant volume, isochloric, at constant entropy. You understand? So we've discussed those ones. So, and where we now further to, it was engineering devices based on steady flow. So when we talked about steady flow, ideally we are considering an open system. Is that taken? An open system, and it may later result to an adiabatic. The process can also be adiabatic in nature. Is that taken? So it can be adiabatic in nature or totally, yes, it can be adiabatic in nature, but it cannot be totally isolated, because there's still the transfer of materials or matters in that case. So in our previous class we looked at the continuity equation, where we say that U1, which is internal energy, specific internal energy, and C1 square over 2 plus Z1G plus P1 V1. Don't forget, we have capital letter V and we have small letter v. This capital letter V is normal volume, while this small letter v is specific volume. Is that taken? Specific volume, small letter v is equal to capital letter V over m. Is that taken? So this one is now what? P1 V1. This is what? Flow work from, what's it called? Boyle's law. So P1 V1, and then we have the applied heat is equals to W, which is the work that will be produced, plus U2 at the outlet. We have the inlet at the exit, so the U2 is the exit, then plus C2 squared over 2 plus Z2. The Z is the datum, that is the height from the above the datum, Z2. Then we have P2 V2. Is that again? And don't forget, we considered the continuity equation, where we have the mass flow rate is equals to CA over specific volume. Is that again? We've derived it in our previous class. Now today we want to look at energy balance for a steady process, a steady flow process. Is that again? So we want to look at energy balance for a steady flow process. So like we have it here, is that again? So you can as well write this equation. It's from this equation, the above equation. Is that again? Just that every other one here, as in the U, C, Z, P, is that again? They are all energy, but we are going to multiply them by their mass flow rate. Is that again? Mass flow rate. Since we said that it is a steady flow, you understand now? It simply means that m dot is equals to m1 at the inlet is equals to what? M2 at the outlet. Is that again? What I'm saying is this: if you have an open system, like this, is that again? So here we've considered the diagram. This is Z2, this is Z1, as in the height of this the outlet, the above to the datum, You understand now? So here mass is being transferred. Mass moves from here to what? To here. You understand now? Since mass is what is transferred, it simply means that the same quantity of fluid that enters will be the same quantity of fluid that will come out. So m dot is the same thing. So here I'm going to I will exclude the w and the what and the q. So here I'll have m dot into brackets u1 plus c1 squared over 2 plus z1 g plus p1 v1, is that again? So plus q is equals to m dot, then we have u2 plus c2 squared over 2 plus z2g, is that again? So and we have p2 v2 plus w, which is the work done. You understand? But don't forget that your enthalpy is equals to internal energy plus PV. That's the what? That's the enthalpy. So I can write this one as U1 plus P1 V1 to be equals to what? To equals to H. You understand now? So if I do that, I will have my M dot is equals to H1. Is that okay? Meaning that I've brought this one and this one together. Then I will have C1 squared over 2 plus Z1G, then plus Q is equals to M dot, then we have H2 here, understand? Then plus the C2 squared over 2 plus Z2G. Are you there? Then plus W. Is that understood? Now, also, let me change the pen right to not look boring. Okay. Also, we have this one is potential energy, this is kinetic energy. Is that again? Potential energy, kinetic energy. So if you come up here, this is what? The change in internal energy, and this is what? The change in flow pressure, or whichever term we name it. You understand? So delta U, capital letter, in this case is equals to plus delta potential energy plus that of kinetic energy, change in kinetic energy, plus change in PV, then plus W. Plus W. Okay, we are considering the what? The distance. So here now is equals to where your change in U is known as change in internal energy. Is that again? But in this case is not per unit mass. Is that again? So it is not a specific internal energy, but it is just what's changing internal energy. Anything that you have and you divide by what? By mass, it is what? It is regarded as what? Specific something. You understand? Normally enthalpy is capital letter H, but divided by M will give you what? Small letter h. You understand? So here having this now will give you small letter u. You understand now? Which we have up here, as in this small letter u subscript 1 here. So now back to this now. This one is now what? Mass flow rate into brackets u2 minus u1. Don't forget that this is change. You understand now? This is change. So as in you bring this one, so this equation equals to q. You understand? It's as if this one is here, then you move everything that you have here. Let us move it to the other side. If you move them here, know that sign will change. You understand? This one remain as this. Now that's the reason why we have what this one P2 V2 will now be minus P1 V1, which you have as what changing PV. Then we also have that of kinetic potential and the internal energy. I hope that is clear. So here, so same thing goes to potential. Changing potential energy is equals to m dot z2 minus z1. So G will be here. We have what's it called, G here. You understand now? So G will be there. I hope that is clear, because this one is what m z1 G, then this one to m dot z2 G. So we also have that of kinetic energy, which is equals to what m dot C1 squared over 2 minus 2 BS, then C1 squared over 2. Is that taken? So we have this one to be changing kinetic energy. And finally we now have what changing PV, which is tend to be the change in energy required to move the fluid. So this is the energy required to move the fluid. So m dot, that's P2 V2 minus P1 V1. Don't forget the V is small letter specific volume. Is that taken? So that's just it. So this one is now what the energy required to move the fluid. Is that taken? Here now the fluid is going to move, so the energy that is needed to move the fluid, that is your PV. You understand? So we have that. Now in a case whereby we have our Z, which is potential energy, we have what's it called, enthalpy. You get? So here, this change in U and this, okay, I can rewrite it as Q is equals to do something. No, this is change in U and this is this, and we have established this formula here that H is equals to U plus what's it called, PV. You understand? So PV so here now we can now have the formula to be written as Q. So Q is equals to change in potential energy plus change in kinetic energy plus change in PV plus W plus change in internal energy. But because the change in internal energy and the PV is that taken, we can change them to what to be H. So this one will now be Q is equals to change in potential plus change in kinetic plus work done. So this one and this one will now become what change in H, which is the enthalpy. That is the enthalpy. Is that taken? So if we now have this one is for what, for a flow, steady flow. But what in a case that we now have a flow, this is for what, for steady flow. So in a case that we have what, non-flow, non-flow process. So for a non-flow process, is that again the only thing that we'll be considering is what? Q, which is the heat applied, then change in U plus the final outcome. There won't be potential nor kinetic. Is that taken? So now let us now go to another device, which is part of engineering steady flow devices. We want to look at the case of nozzle and diffuser. So we have a nozzle and diffuser. So what is a nozzle? A nozzle and diffuser are commonly used in jet engine, rockets, spacecraft, and some other. This even in house garden hose. Is that again? In garden hose, they normally use what? The application of nose there. So they are properly shaped. They are ducts. Is that again? And they are what? They are properly shaped and are used to increase or decrease the velocity as well as what? As well as the pressure. You understand? So based on diagram, this is a nozzle. This is a nozzle. This is a nozzle. Nozzle. It flows in and comes out. You understand? So a nozzle works based on adiabatic process. It is work based on adiabatic process. When we said at adiabatic process, it simply means that your Q is equals to 0 at adiabatic process. So that's the principle. That's the principle. So the formula for the nozzle, as we are writing it from here now, so it is a flow, not non-flow. This one is just for non-flow. So it is a flow. Then what we are going to have here, since it is this, we are going to have Q. You already know the summation of energies that we have. We have Q. We consider our mass flow rate. Then you have H2 minus H1. Me saying that I've considered U and PV. Is that taken? So that's the reason why I put them together. You get? So I'm sorry. All right. So we have mass flow rate. So I use this larger bracket plus, we have U, potential, kinetic. Which other one do we have? We have potential, kinetic, okay, PV. So we have PV here. We have PV. Thank you. Okay, so we have potential, kinetic. So here we should consider the kinetic. The kinetic is half the C2 squared minus C1 squared. Is that taken? So let me put this in brackets. So the half is affecting both of them. You understand? So that of kinetic, potential energy as m dot, okay, G will be here. That's Z2 minus Z1. You understand now? So in this case, so for a nozzle, one thing is that it does not have shafts, so there is no work done. The work done is equals to 0. Is that taken? We'll still consider that. Then we have the work done. So here now I can have my Q is equals to m dot, that is H2 minus H1. Don't forget your H2 minus H1, that's the change in everything that you have here. So plus 1 over 2 C1 C2 squared minus C1 squared. You understand? So this, if Z1 and Z2 are negligible, is that meaning that you are taking what Z1 and Z2 to be equal, or they are equal to what? To 0. And we've already known that. And W is this guy, and the work done, since there is no shaft, the work done is what? Is 0. You understand? And don't forget that this thing, it occurs at adiabatic condition. So when we say adiabatic, it simply means that your Q is also 0. Your Q is also 0. You understand? So here now, since you have this bigger bracket, is that taken? So you are going to have this one is equals to 0. You bring this one here, it becomes minus m dot h2 minus h1. Is that taken? This m we cancel, we multiply this, is equals to half, then m dot, that is c2 squared minus c1 squared. You understand? So m dot we cancel what? M dot. You understand? You can easily say that h1 minus h2 here, you understand, is as if you were to clear the brackets. Minus times plus is minus, this you still have it here, then minus times minus give you plus. That's the reason why you have this one. This is an advanced course, I don't need to be explaining that. So this one is half, then you have c2 squared minus c1 squared. So this is the formula for both nozzle and diffuser, the nozzle and the diffuser. Now let us explain the engineering aspect of it. For this nozzle, is that taken? You know that this is the inlet, this is V1, this is the outlet, this is your V2. Is that taken? So in this case, your V2 is greater than V1 in case of nozzle. Please take note. In case of nozzle, your V2 is greater than what? Your V1. In case of what? Nozzle. For nozzle, V2 is greater than V1. Is that taken? As V2 increases, is that taken? Now, what happens to internal energy? Enthalpy. Your enthalpy, your H1 will be greater than H2. So the reverse is now the case for the diffuser. So the diffuser, the diagram is this. This is the diagram now. You can see that nozzle, its cross-sectional area decreases for nozzle. Cross-sectional area decreases, but diffuser, the cross-sectional area what increases. This is a diffuser. Is that okay? This is your inlet, this is V1, and this is your outlet, then this is V2. In this case, your V1 is greater than V2. Please take note. And another thing is that your H2 is greater than H1. It's as simple as that. You understand? So if you have any question on nozzle and diffuser, you will be able to handle that. But please take note. You can only use this provided that you were told that the datum, as in the height, your Z1 and Z2 are negligible or they are equal. That's when you can apply this. If they are considered, then you include it in your formula. You understand? You now add plus, then m dot, then Z2 G minus m dot Z1 G. It's as simple as that. Okay. Another thing we need to consider is turbine. It is turbine. So turbine is also an application. Turbine is also an application. We have turbine and we have compressors and pump. You understand? So it's also an application of steady flow. So for the case of what of turbine, you understand? So it is still the same principle that we use to derive the formula of the other one. So a turbine is a device with rows of blade. It is a device with what? With rows of blade mounted on a shaft which could be rotated about its axis. A turbine is what? Is a device with rows of blade mounted on a shaft to cause rotation around its axis. You understand now? Like the one that they use in what? In the dam, which is hydroelectric power station. You understand now? So this is the diagram of a turbine. A turbine. Okay. So this is process 1 and 2, inlet and outlet. This is the what? These are the blade. The blade is what will be rotated. You understand now? So considering the same formula that we used the other time, so we have Q is equals to m dot, then we have H2 minus H1. This formula is not new to us again. So Z2G minus Z1G plus the kinetic energy. I can put 2 outside here. So here now is that taken plus work done. There will be work done. It has shafts. Is that taken? Since there is shaft, it is nozzle or diffuser that did not have that does not have shaft. But a turbine what has a shaft. So work done will be what will be produced. So here now I can have my Q minus W. Is that taking this one to the other side? Then this one is equals to. Now let us now consider that Z1 and Z2 are negligible. If they are negligible, it simply means that we are going to what? We are going to remove them from this equation. If we exclude them from the equation will reduce to H2 minus H1, then plus 1 over 2, then C2 squared minus C1 squared. Is that taken? So that's the case of turbine. Is that taken? Now if it now occurs at adiabatic, is that taken? If adiabatic is involved, anywhere adiabatic is said, it simply means that what? Your Q is equals to 0. You understand? If my Q is equals to 0, I'm going to have my W, it will not be negative, is equals to m dot as H2 then H1. Is that taken? Plus half m dot. I've cleared the bracket now. This one has its own m dot. Now this one to m dot, then I have C2 squared minus C1 squared. So we have this. You understand now? So you can maneuver and remove this. If I'm to remove this, is that taken? I can have my W to be m dot then H1 minus H2. Is that taken? Plus half m dot, then this one becomes C1 C squared minus C2 squared. I've not done anything, I only removed the minus. Is that taken? So this is the formula for what is it called? Turbine. Yes, as the case of turbine. Now what is the case of compressor? I want us to consider all the devices, then we go into questions. You understand? So another one is what is compressors and pumps. You know, compressor is used to it is used to compress, and it is used to increase pressure. It's a device that is used to increase pressure of gas or fluid flowing through it. You understand? So compressor has inlet valve and the outlet valve. Is that again? The inlet valve, that's where it sucks. Then the outlet valve, that's where it pumps. It sucks the gas and pumps it out. You understand now? So the most applicable one is the rotary compressor and reciprocating compressor. So compressor is just what opposite of turbine. Compressor is the opposite of turbine. Is the opposite of turbine. You know, in the case of turbine, look at it. The cross-sectional area increases, but for that of compressor, is that taken? The cross-sectional area decreases, as we have it in case of diffuser and nozzle. So it increases, sorry, it decreases now. You understand? It decreases. This is compressor, this is turbine. You understand? So that's, it uses the same formula. It uses the same formula as we derived the other time. So another special device we now have now is okay, case, we can have a case whereby they say that your velocities are negligible too. Just know that if the velocities are negligible, then this one will remain your what? Your formula. If velocities are negligible, so our W becomes what? M dot, that's H1 minus H2. Then we have it that way. So the last one among the devices, it is throttling device. Throttling device, which is throttling valves. What is a throttling valves? Is that again? Now let us consider, because this is thermodynamics, we have, let us use refrigerator as a case study. Is that again? Refrigerator has what's it called, components. One of it is compressor. We have considered it. It has evaporator and condenser. If you are considering those ones under thermodynamics or heat transfer, is that again, we will call them heat exchanger. You see, what's it called, evaporator and condensers, they are heat exchanger. They are heat exchangers. They exchange heat. They are heat exchangers. But here now, so among apart from the compressor, condenser, evaporator, is that again? So the other one we have is now what? Throttling device, which is generally called expansion valve or capillary tube. Is that it is a tiny valve. You understand now? So majorly its purpose is a valve used to cause pressure drops, because the pressure that is coming from whatever where it is coming from, is that with high speed. Do you understand? And the purpose of this what throttling valves is to reduce the pressure, so it will cause what? A pressure drop. You understand now? So the diagram of this thing, the diagram has to be mastered. All the diagram that I've considered, you have to master them. Understand now? Okay, let me clean this. Okay, perfect, wonderful. All right, so here, then it enters, then comes out here. Understand? So there are process 1 and process 2, or you call it stage 1 and stage 2. This is a throttle valve. You understand now? So the formula for a throttle valve is simply your Z1 is equals to Z2. If you consider it in that thing, it will be 0. So work done is 0. It works under adiabatic condition. This is 0. We understand now? If all these are zeros, what do we have left? So from here, the work done is 0. So which other one? Okay, so we have H and C. So in that case, so we are going to have our formula to be M dot it is H2 minus H1 is equals to m dot. So we have C1 squared, okay, 1/2 will be here, minus C2 squared. You understand? So this we cancel this, so we have H2 is that taken, then minus H1 is equals to half is here, half, it is C1 squared minus C2 squared. So this is the formula you are using to solve a question on throttle valve. You understand? If they also say that, okay, fine, your C1 and C2, if C1 equals to C2 or both are negligible, then it simply means that H2, it is approximately to H1. They cannot be exactly the same, but approximately the same thing. You understand now? So that's the condition for throttle device. Okay, so I think the next thing in our next video we're going to consider problems for us to solve. Thanks for watching. So look out for more questions and other topics under thermodynamics as far as MEE 202 is concerned. Thank you. Like, share, subscribe, follow.